All right, we are going to look at Unit 1, Section 1. Unit 1 is a chapter on limits. So here are the key skills. Students can find limits using tables and graphs. You don't know what a limit is, but I want you to understand we're going to have to find whatever these are through tables and graphs. We're also going to have to find them analytically. Analytically means using algebra skills. So multiplying, dividing, rational functions, square rooting, things like that. So those first two have to do with limits. This third one's also limits. Describe infinite limits and limits at infinity. So we need to be careful and understand the notation and difference between those. And then also here in the middle is describe continuity and removable and non-removable discontinuities. So here are the four key skills. And really, we have this one, we have limits, and then continuity and discontinuity. Those are the key things in this chapter. Now, there is some algebra work, but mostly this is conceptual. You just need to understand. So these are brand new skills. It's almost like teaching you a new unit in science. It's not like there's a lot of skills or math involved. There will be some math, of course. But it's more, do you understand what's going on? Can you recognize? And so as we go through these notes, if there's something you're not sure about, if there's something that doesn't make sense, mark it so that we can discuss it when we come into class. Section 1.2, finding limits graphically and numerically using tables. So let's start by understanding what a limit is. A limit is a way to say as x approaches a value, let's say 3, f of x approaches what value? So in essence, that's the question we're asking. When I say what is a limit, and that limit will be defined as x approaches some value, what does f of x, or think y, equal? So if we were to take a simple graph and say this is y equals x, so as x approaches 5, what does f of x approach, or y equal? Well, I know in this, when x is 4.9, y is 4.9. When x is 4.99, y is 4.99, because our equation again is y equals x. So as I get closer and closer to 5 on my x, what does my function, or y, get closer and closer to? Well, that also gets closer to 5. Now, if we had a function, let's say y equals x plus 3, as x approaches 5, what is this function? Sorry, let me use function notation here. What is this function getting closer and closer to? Well, as we get closer to 5, so here's 5, this is going to be 8. The point is 8, so I know the function is going to get closer to 8. And that is the essence of the limit question when we're looking at a graph or a table. And that is the concept, as our x values approach a certain value, what do our y values approach? So let's take a look at this one. Now, in this table, we're going to see x approaches 1 from the left and x approaches 1 from the right. So here is our f of x. So as x approaches 1 from the left and x approaches 1 from the right, 0.75, 0.9, 0.99, 0.999. Notice these x values are getting closer to 1 from the left of 1 We have 1.001, 1.01, 1.1, 1.25. So going backwards, these approach x from the right. What are these values approaching? 2.997, 3.003 are the ones closest to this. Well, it looks like it's approaching 3. Now, can 1 equal 3? So if we tried to plug 1 into this function and found f of 1, we would have 1 minus 1 over 1 minus 1. Well, that's 0 over 0. And that doesn't work. Okay? This is called indeterminate form when you have 0 over 0. And that means you can do something about it, but it's not the actual limit. If we look at the graph of this function, we see a hole right here at 1, 3. So on the graph, if, as you come from the left, let me change colors or marker here, pen, as I come from the left, I approach 3. As I come from the right, I approach 3, but it doesn't actually equal 3, then this limit can exist. So it doesn't mean, so f of 1 does not equal 3, but the limit of f of x as x approaches 1 equals 3. So this limit exists even though the function doesn't exist at that point. And that will show up a lot, okay? So here's the notation. The limit of f of x as x approaches 1 is 3. And we use this a little bit in pre-calculus so that you are familiar with that notation. Often we used it in conjunction with end behavior. So we had limit as x approaches infinity. The limit of f of x as x approaches infinity, and we said what that end behavior was. So here's our informal definition of limit. If f of x becomes arbitrarily close, that just means super close to a single number as x approaches c from either side, then that limit exists. So this section says finding limits graphically and numerically. Numerically means by using a table, by putting different values in and just checking. So here we have a function, x over the square root of x plus 1 minus 1, and we want to check values near 0. Okay, now if I plug 0 in, I'm going to get 0 over the square root of 1 minus 1. That's 0 over 0. Every time we do this, I want you to put indeterminate form. All this means, what this means, indeterminate form, is that we cannot tell. This limit doesn't actually equal that. It just means we can't tell what it is. Maybe the limit exists. There are cases where limits don't exist, and we'll talk about those later on. So what they did is they created a table on their calculator, or showed how you could do that. You type this function in, and notice the x values that they're putting in. You're just getting closer and closer to 0. So zeros are error because it can't equal it. And so 0.01, 0.02, 0.03, and then negative 0.001, 0.002, and negative 0.003. Now, looking at this table, what value are we getting close to from both sides? So as x approaches 0 from the right, it approaches 2. And as x approaches 0 from the left, it also approaches 2. So we could say with confidence that this limit equals 2. Again, the function doesn't equal 2, but the limit does. Okay? And we can also do it graphically on the calculator by graphing the function. Plug 0 in and see that it's undefined, and there's a trace feature on your calculator, it's to the left of the graph button, and you can just push your left and right arrow and see as you get closer and closer, watch these y values and see what happens. If you see something like this and you have 1 e to the negative 4, that just means, that's scientific notation, 1 times 10 to the negative 4 is 0.0001. So again, really close to 0. Okay, so here is an important note, and I've stated this already, but note that the function is undefined, and yet f of x appears to be approaching a limit as x approaches 0. This often happens because we'll give you problems where the equation doesn't exist. The existence or non-existence of f of x at x equals c has no bearing on the existence of the limit of f of x as x approaches c. What that means is the limit can exist when x approaches c. C is just a stand-in for some value, even if f of x does not equal c. Okay, so that's what that means in less mathematical terms. Now, as we go through these notes, I've not required you to fill in a lot of blanks. You're just understanding this. So I expect you to mark these up, underline these key statements, rewrite this, do any practice that I may have you do here. That's what I'll be checking when I check these notes, to see that you are engaged and involved. Because again, it's not just filling in the blanks, it's understanding. So find the limit of f of x as x approaches 2, where f of x equals 1 when x is not 2, and f of x equals 0 when x is 2. So we have this graph right here. Again, this is a piecewise function. So that means we have to figure out what the graph looks like. So it's 1 everywhere except right here at 2, it's actually equal to 0. Okay, so let's check. As the function, as x approaches 2 from the left, the function is approaching 1. And as x approaches 2 from the right, our function is also approaching 1. So the limit of this, and it states it here, I'm going to write it in notation, the limit of f of x as x approaches 2 equals 1. Again, does f of x equal 1? Sorry. Does f of 2 equal 1? No, it does not. These do not equal each other. But again, from our note above, that does not matter. So let's take a look at this one. Limit as x approaches 2, x squared minus 3x plus 2 over x minus 2. I would like you to do that problem on your own. Get a graphing calculator or on your computer, type in this function, find these values, and see what the limit as x approaches 2 equals. We will note that if you plug in 2, that is 4 minus 6 plus 2, which equals 0, and 2 minus 2 equals 0. So this would be indeterminate form because the numerator and denominator both equal each other, or both equal 0. Because the numerator and denominator both equal 0, this is indeterminate form. All right, now there are 3 cases where limits fail to exist. Okay, this is different right and left behavior. So we know how we checked x values from the left, or as we approach an x value from the left and from the right, the function has to equal the same thing, or be approaching the same value. So we're going to check this value here, the absolute value of x over x, and to do that we're just going to graph that. So when x is positive, that would be like 1/2 over 1/2 Well, that equals 1. And so we have a graph that goes like this. Maybe a straighter line if we can. Third time's the charm there. Now note, this is not equal at 0. 0 over 0 does not exist. But when x is negative, like -1, we'd have -1 in absolute value over -1. So that's 1 over -1 or -1. So as x approaches, the limit as x approaches 0. Now I'm going to jump ahead and say, give you this notation. This negative in this limit notation means from the left. Okay, that means from the left going this direction. So the limit of f of x as x approaches 0 from the left equals -1. And the limit of f of x as x approaches 0 from the right, our symbol is a plus sign because it's from the more positive direction up here. That equals 1. So if our right and left behavior do not equal each other, so if the left-sided limit and the right-sided limit do not equal each other, this limit does not exist. Okay? Unbounded behavior. Okay? So if we were to graph this, 1 over x squared, it would look like this. So 0 is an asymptote, and it continues on forever. And so as x approaches 0 from the right, it is not going to equal a single number because it's going to continue to increase. The closer I get to 0, the further this will go up, and it will approach infinity. Now later we'll use some notation to communicate that fact, because that is important information that we can utilize. But for now we're just going to say the limit does not exist. Oscillating behavior. So here we have the function sine of 1 over x. And we have 2 pi, 2/3, 2 over pi, 2 over 3 pi, 2 over 5 pi. And so you notice that this is switching between 1 and -1 very quickly. And this is the graph. So it's hard to tell in this graph, but this graph is switching from 1 to -1 so quickly that this limit will not exist. So you can, as you get closer and closer, this is going to jump between +1 and -1 even more rapidly. So even as you get closer and closer to 0, you can always get a little bit closer and switch. So it's not approaching one single number. This limit does not exist. So again, 3 different ways the limit fails to exist. Different right and left behavior. Unbounded behavior, meaning we're going to infinity, or maybe to a negative infinity. And oscillating behavior. These 2 are the most common ones we'll work with, but it's good to be aware of the oscillating behavior one. All right, now we're going to cover the formal definition of a limit. Now, as I cover this, I want to make sure it is clear why I am covering this. This is the formal mathematical definition of a limit. When I went through college as a math major, I had a lot of math classes. And in college, you're going to see a lot of formal definitions in those college math classes. And I did not have as much exposure to these formal definitions, and so it took me a lot of work and time before I could understand what was going on. Not all of you will need to know this or be familiar with these formal definitions, but I'm not just preparing you, I'm preparing all of you, and some of you may. And so when we get to these formal definitions of a limit, for some of you, if you don't understand it, that's not going to be a super big deal. This is not something that's going to be on the test, but I do want you to have exposure to it. So we've talked about the informal definition, just as x approaches a value, f of x approaches a single number L from both sides. Okay. We have not talked about what it means for f of x to become arbitrarily, the book used that, arbitrarily close to L and x approaches C. So these are the things that we're going to formalize in this definition. So first person to assign the mathematically rigorous meanings to these two phrases was Cauchy. Cauchy was a mathematician. I don't know where he was from. And this is the epsilon delta definition of a limit. Now we will see that, you'll see that in future math classes a lot, those of you who take. So epsilon, whenever you see this, it's a small Greek letter, it represents a small positive number. I can't tell you how many classes where I was doing proofs, it has always said, all right, there exists an epsilon, and everybody knew that it just represented a small positive number, and super small, like as small as you want, as small as you can get. And it's just some arbitrary small number, meaning it doesn't exactly have to be one specific number. So f of x becomes arbitrarily close to L. Sorry, I missed the L there. That means that f of x lies in between. So I'm going to go like this. L plus epsilon, L minus epsilon. And that's what we see here. Here's our limit. This is our f of x value that we're approaching. And it's within this bound. So let's say that this was 5 and epsilon was 0.00003. So that means I can get between this value between 5.00003 and 4, no, that's my problem. Sorry, 4.99997. So I can get the limit between those values, choosing this very small positive value. Okay? So that's what arbitrarily close to L means. Now, x approaches C means that there's this positive number delta, lowercase delta, looks like this. I drew that a little bit too far. It's like an L, like an 8 I mean, but it doesn't close all the way. That x lies in the interval C plus delta and C minus delta. And that's what we see here. We have the C plus delta and C minus delta. So as our x approaches this C, as it gets within this small interval, then L gets within this small interval. That's all we're saying. That's the formal definition. Well, let me write it for you. When we write formal definitions, we're going to have to make our statements. Okay? Set our grounds. What are we dealing with? So we're going to say let f be a function defined on an open interval containing C except possibly at C. So all this says is we have a function that's defined over this open interval, doesn't have to be very big, containing C, except it may not be defined at C. And let L be a real number. Then the statement, the limit as x approaches C of f of x equals L means, so we're defining this. We're defining the statement, the limit of f of x as x approaches C equals L means that for each epsilon greater than 0, there exists delta greater than 0 such that if x minus c is between 0 and delta, so just we got close enough within that delta range, then f of x minus L is less than epsilon. Okay? Now I would like to point out this line here. This line repeats itself in so many proofs that there are symbols for these. There are mathematical symbols, shorthand notation, if you will, for this. So I could rewrite that saying, for each, this is the symbol, for each or for all or for any epsilon greater than 0, there exists delta greater than 0 such that, and this says the same thing as that. Okay, so that's shorthand notation that I may use just so you get familiar with it. Anyways, that is section 1.2. Thank you for watching.